Okay, so we've got a beam with a magnet on the end of it. I'll use this to demonstrate. And we've got this thing, I don't want to rotate this at 180 centimeters per second, you can knock a tooth out. But imagine 1,001, 1,000, okay, that's about 4 radians per second right there. Now this magnet on the end, the question is, how fast is that magnet moving? Okay, and how fast would it be moving if that was going about 50% faster? So the answer is fairly simple. Let's assume that the angular acceleration is negative 0.06 radians per second squared. Reasonable enough. Means if it's at 6 radians per second, it's going to take 100 seconds to come to rest. Well, we know the acceleration is less than that because we know that thing's going to keep going for more than 100 seconds. It's probably more like negative 0.01 radian per second squared. But it isn't 0.06. And let's say omega is 6 radians per second. Say at the instant I release it. And at that instant, we want to say t equals 0, so theta equals 0 radians. And t equals 0. Well, from this, with this information, we could write out the function for theta. We could write out the function for omega. Okay. Now, of course, the function for alpha is pretty simple because that's it. Because it doesn't have any t dependence, right? So among other things, we could write kind of got a bunch up. There's our equation for omega. Our equation for theta is this. Okay. Now, since I said that all this applies at t equals 0, then we're going to say theta naught is 0, omega naught is 0, and so forth. Okay, so the motion of this thing is solved. We can answer any question we want about the angular motion of this system. How do we relate this to the linear? Okay, so what's the speed of the magnet? Well, V naught is, well, 6 radians per second, but a radian is 30 centimeters along the arc. The radian is equal to the radius. So we could say this is six radians per second multiplied by 30 centimeters along the arc per radian. That's a formal calculation, but you shouldn't be able to just look at this and say, okay, a radian 30 centimeters along the arc. Okay, that's 180 centimeters per second. And of course, theta naught is 0 and alpha is this. And so the acceleration, it's an A, meaning it's along the arc. We can immediately see it. If it's 0.06, negative 0.06 radians per second squared, means it's 0.06 30 centimeter increments per second squared, with negative 0.18 radian centimeters per second squared. If I can write it out, I don't have to use the formulas to write these out, but I should check it with the formulas to be sure. I should understand both ways, by the formulas and just by the meanings. Okay, so A is what? It's negative 0.06 radians per second squared times our good old 30 centimeters per radian equals negative 0.18, and you want to put that 0.18 in there, but I don't want to write it that low on the board. Okay, negative 0.18 centimeters per second squared. Okay, now let's assume magnet mass 50 grams. What's the net force? Net force from the magnet is what? Write it out for me. Okay, we've got a dramatic moment coming up here. So net force of the magnet is net force equals MA. These are vectors. And that's going to be really important here because we understand that, okay, if this thing's going around here and slowing down, then the magnet, when it, let's say, passes this point here, is slowing down, which means there's a net force. Part of the net force anyhow is in this direction, but the one net force people want to neglect here, yeah, of course, everybody neglected it when I said the problem. So your answer is exactly what I expected. It would have been well impressed and not too surprised if somebody had thought about the other forces, okay? And some people did, you know, some people have a free body diagram with the gravity and the normal force. Okay, so that's a good start. There's one other force that people are forgetting. Okay, so part of your net force is slowing this thing down. But this thing is not moving along a straight line. It's curving. Okay, so there has to be another force that causes it to change its direction. This force doesn't cause it to change its direction. What force causes it to change its direction? Well, I pretty quickly got an answer when I posed that question. It's the centripetal force. Okay, so I'm going to say your acceleration is the force parallel, and it's not the force due to the parallel force. It's the parallel acceleration plus the centripetal acceleration. Now, the parallel, a parallel means a parallel to the line of motion at any given instant. This is not constant. Okay, this is not arc tangent, means acceleration tangential. So I'm going to actually write out the word, but I'll abbreviate it. Tangential means, well, tangent to the path. Okay, now store that away because you're going to be in multivariable calculus here in a little over, a little over 2 months. Okay, well, the first thing we're going to be looking at is this sort of thing. Okay, so it's important for 2 reasons. Whatever your path, at any given instant, there's a tangent line to that path. And your velocity is along that tangent line. Tangential velocity. Very easy to calculate if you parameterize your curve, stuff like that. We might do a little bit of that here. So something you want to be aware of. Okay. And the centripetal acceleration is radial. It's toward the center, right? This is tangential. Well, the tangent line and the radial line are perpendicular. Okay, the radial line goes from the center out to, in this case, from the center out to the path, or from the center out to the magnet, wherever it happens to be. And did I say radial? Yeah, I mean, I think I said it right, but radial goes from the axis of rotation out to the point where the magnet is. And the centripetal force is like this. And wherever they go, they're perpendicular because the arc is always perpendicular to that. Okay. They're perpendicular by simple geometry. And when we get into multivariable calculus, you'll see it more formally. That's the easy part of multivariable calculus. So you won't have any trouble with it. We'll save that though. We'll formalize it later. Okay. So tell me now, work it out. What's the magnitude of your acceleration here? And what's its direction? Now, the direction keeps changing in space. So let's say, what's its direction compared to the tangential direction? What angle does the acceleration vector make with the tangential vector? Okay, so find the magnitude . I'm going to say the magnitude of A with A tangential. Call that angle phi. Greek letter between phi and pho. Okay. Yeah, phi, phi, pho, pho. Yeah. See if you can work that out. What are you going to have to do? Okay, well, we easily got the magnitudes for the tangential and centripetal acceleration. Okay. And centripetal acceleration is just v squared over r. So I'll just make a little. And v is 180 centimeters per second. You square that, you get 324 centimeters per second squared. Okay. And then you divide that by 30 centimeters and you get 1,080 centimeters. It's at 324. It's 32,400 centimeters squared per second squared. Okay. Or 3.24 meters per second squared if you want to go to SI units. And then you divide that either by 30 centimeters or 0.3 meters, and you get 1.08 meters per second squared or 1,080 centimeters per second squared. You're going to be able to answer the question either way. Now, when you come to doing forces, you might decide on which system of units you want. You want to do it in centimeters and seconds? Yeah. Okay. Want to do it in which case you would use your mass in grams and get ergs. You get dynes of force, ergs of energy. Okay. And we don't usually work in that system, but it's an equivalent system. We usually work in SI, so we probably will end up in SI. Right now, it doesn't matter. Easy to convert. So magnitude of A is square root of is some of these squares because these things are perpendicular. Pythagorean theorem applies. Well, that's still 1,080 centimeters per second squared. There's some decimals out there. They'll change a little bit, but this is like 1/5,000th of that. So, okay, so that square root's going to be like 1/10,000th off of that. So it's going to be 1080.01. Okay. I think, I don't want to think that hard right now. Okay, and then theta. Is the arctangent of got to draw a picture. I got that wrong. So I should have had a picture so we can write that out. I might still have it. It's tangential over its centripetal. Here's your picture. Okay, so here's your axis of rotation. Here's your magnet at whatever position. Here's your radial direction, which I should have labeled on the other side. Okay, let me do it right. Here's your magnet. Here's your tangential direction. And here's your radial direction. Now here is your tangential acceleration. And here is your radial acceleration. So here, distinguish it with a slightly bigger color. Here's your acceleration. The angle is theta. And that angle is going to be the arctangent of your tangential plus over your centripetal acceleration. The angle being greater than 90 degrees, the arctangent gives you a number between negative 90 degrees and positive 90 degrees. You're going to have to add 90 degrees to whatever you get because the angle's 90 degrees. So you understand the trig, and if you don't, make sure you check it out, come and ask me, whatever. Okay. So the theta so I'm going to say theta is the arctangent of this. I said plus 90 degrees, it's actually plus 180 degrees. Things get a little confused with the direction. I'm just going to say I don't want to go into all the detail of that. Theta is going to be the inverse tangent of 0.18 over 1,080 centimeters per second squared over centimeters per second squared. So I'm just not going to write that out. Units clearly flying out. So it's about that. Which is it's going to differ from 90 degrees by this many radians. Well, we can work that out. It's going to be a really small angle. That many radians times like 60 degrees is going to give us like one. I'm going to say very approximately 90 degrees minus 0.001 degrees. But because the arctangent is only accurate up to plus or minus, okay, and a couple of other things I don't want to get into, it's going to be 0.001 degrees on the other side. And you can impose a coordinate system, temporary coordinate system, auxiliary coordinate system here, and work it out within that coordinate system. An x-axis this way, a y-axis this way, and work out the arctangent. I just don't want to go to that much trouble. I've got some approximations in there that I'm not totally sure of, but it's like 90.001 degrees. What you need to understand is that in other situations, like if you're driving your car around a traffic circle and speeding up, then you have an acceleration in your direction of motion and an acceleration toward the center of the circle. If you're coming around the traffic circle, about to make a turn, you might be slowing down, in which case you'd have a tangential acceleration toward the, behind you, direction opposite your motion, and still a centripetal acceleration toward the center. And your picture would be more like this if you're slowing down, and your angle would be on the other side of 90 degrees if you're speeding up. Okay. Now, the formal ways of calculating these using vectors and vector functions is much simpler. So, okay, so anyhow, there we have that. Now, really want to just get you thinking about these so I can ask the hard questions. Okay. What if this thing is not only rotating, but I'm moving it along this way? Maybe accelerating, maybe at a constant velocity. What can you do with the velocity of the magnet? Okay. Like say, well, the center of mass of the system, or let's say the center mass of the system is moving with some additional velocity. Before I do that, let's calculate the force. Okay, so the force Well, now I'm going to invoke I and J vectors. Probably should have done it before I did this. Okay. So here we are at an instant. Our I and J vectors are in the direction of motion and in the direction of centripetal acceleration. So we have I and J vectors in the direction of motion keeps changing. Our coordinate system keeps changing, but in any instant, we temporarily have a coordinate system, which in multivariable calculus we find is really easy to calculate. Okay. Not going to worry too much about that right here. So we're going to say that that's then approximately 50 grams times this, converting to metric units. It's going to be 0.05 kilograms times 10.8 meters per second squared, which is 0.05 times 10 is about half. Approximately 0.5 newtons, okay, times take these into unit vectors. It's going to be like something like this. Okay, this is small enough. The J component's actually going to be a little less than 1 because the whole thing has to be. Actually, doesn't have to be. That kind of works. Okay. Okay. Now the point is, okay, we got this. This might or might not be right. Here, I might not have the right number of zeros. I'm not going to worry about it right now. Bunch of zeros. It's pretty insignificant in this case. In other cases, it might not be. In the cases of some problems you're going to see. Helicopter moving in this direction, blades rotating. Okay. What's the expression for the motion of the tip of the blade? Let's say the velocity of center mass is anything 2 meters per second I plus 3 meters per second J. How are you going to get the velocity function? Okay. Now, problem is this I and J is fixed, this I and J isn't, so it gets a little bit weird. Okay. So we don't have the same I and J here that we had up here. And I want to mention that you have this relative motion. The problem's a little easier than this one to be. If you don't have to sort out the changing direction of the centripetal acceleration. They'll ask you a problem about the centripetal acceleration or velocity or whatever at a given instant. So you don't have to worry too much about the formal setup, okay? But you have to understand that if this thing is, if the incident's pointing at you, it's also, the whole thing's moving in that direction. And I think one of the problems they have is, okay, it's moving straight upward. Then what's happening? You have a motion in this direction superposed to the motion in this direction. You know the magnitude of the velocity down here. And you know the magnitude of this velocity, they're perpendicular, so you just add them as vectors. Okay, I want to go on to another topic. But that should give you some idea of at least a framework of some of the questions you're going to be looking at. Okay. Okay, let's look at a slightly different situation. We'll use the same apparatus here. Okay, here we have the apparatus. Here's a magnet on this side. This thing's unbalanced, so let's accelerate in this direction. Okay. Come back a little bit. And I'm going to drop it. Hopefully the cord's out of the way. Called a simple pendulum. It's not actually that simple. A physical pendulum, I'm sorry. Okay. It's a pendulum motion. When it gets down to low amplitude, you can pretty much model it with a sine of omega t type function. Question is now, how fast is this thing moving when it gets down here? Okay. How fast is it moving if I drop it in a given position when it passes through the equilibrium point? So, schematic. Then I've got some kind of a mass here. And I've got some length. Okay. And I drop it from some distance here. They'll call y. Higher than the center of mass, which implicitly we're going to say is at the center of the beam. Okay, so that's where I've got it set up. That model what we have. Okay, so what's my question is, how fast is it going at the bottom of the arc? Okay. Well, let's discuss it a minute. What do you know? What can you calculate pretty much immediately? Okay, so we have a little trouble figuring this out. So I gave the hint. Think of energy. So I gave you a couple of minutes to think about it. Nobody really had an answer yet, but you're getting there. Okay. So I said, okay, what's the first two things you think about when you think about energy? And so, well, potential energy. So. And at that point, people pretty much told me what's going on. Okay. Then when I say, okay, you got no kinetic energy here, that's right, because you're releasing it from rest. So it's all potential. Good. Okay, now when you get down here. It's down here, then you want to say it's all kinetic. And a little bit, that depends on where you put your zero potential energy. You have that choice. So you want to specify this. Yes, if the zero of potential energy is here, then it's all kinetic. It has to be because the potential is zero. Also, you assume that we have good bearings and so forth. So we're assuming that there's no work loss of friction, no significant energy loss of friction. Okay. Or air resistance or anything else. Just gravity and. Okay, so that's very easy then. You have. Well, it's not totally easy. Because you have what's the potential energy change of the bar? Well, I'll tell you, for any point on the bar, so whatever quark is right there at the middle of that X, or whatever tiny mass increment you want to think about, there's one exactly on the other side. Okay. Now, if this thing rotates, then this thing will be down here, this thing will be up here. Okay, I don't have those. That's too close and everything. All these are equal and opposite, okay? This distance should be equal and opposite to that with respect to the center. Okay, how much does the potential energy of this change? Well, it changes by its mass times this distance, right? And how much does the potential energy of this change? It's this mass times this distance. Now we're assuming the same identical quarks or whatever, identical mass increments, right? So what happens to the potential energy of this? Does it go up or down? Well, it ends up lower, so it goes down. What happens to this one? It increases. It goes up. So you got a mass here going down, a mass here going up, kind of like an Apple machine. Okay. Potential energy doesn't change. Total potential energy. This loses as much as this gains. True for any mass increment on either side. It's matched by mass increment on the other side. And one of them decreases while the other increases. So the net potential energy change of the beam is zero by symmetry. One side goes up, the other side goes down. Just write that down. One side rises, the other side falls. If it's a uniform beam, then there's no net change in potential energy. But one loses by falling, the other gains by rising. Okay. So what that leaves us, it is still potential energy of the mass. And as much as I hate MGH, that's what it is. Okay. I like it because you say it's mg in this direction, gravity doing work in this direction, so gravity does work mgh. And potential energy change is equal and opposite to the work done by the conservative force. You should understand that. Going to need it, especially second semester. Now you're going to need it that couple of weeks. When we get some gravitation. Okay. Yeah. planetary bodies and stuff like that, where gravity does change. You have to be careful about that. Okay. So there's your change of potential. You know, these. The traditional letters for these things are U and K for potential kinetic energy. So that's like U of the mass, U of the beam. Then you get University of Massachusetts and you don't know what to do with that. Okay. I like to be explicit about what these things mean, but K and U are fine. As long as you understand what they mean. Then I think you do. Okay. Well, now we know that delta K is the system. Okay. And this is the delta PE of the system, since the delta PE of the beam is 0. Delta PE of the system is delta PE plus this one, which is just this one in this case. Okay, so delta PE plus delta K equals 0. So that delta K equals mgh. The final kinetic energy is mgh. You know what's the moment of inertia of this system? Because this is a rotating system, you got masses distributed at different distances from your axis of rotation. You got to take all that into consideration, including by doing an integral that you're going to have to do for homework. So we'll talk about it next time. I'm just going to let you do that. Okay. You've already done more complicated integrals in calculus too. So I'm not going to introduce that to you, but we will talk about it next time and try to put it on really a firm foundation. Fair enough? But it's a simple integral. The simple integral for this is that the moment of inertia of the beam plus the mr squared for this. What's r? Is half the length. And it give you r, I gave you L. And you understand, of course, that this thing's constrained to move the distance L over 2. So that's what you get. What's the moment of inertia of the beam? About the center, it's 1/12 ml squared plus then little ml squared over 4. That's not a formula to memorize, that's just a formula that applies to this situation. But you understand that if I give you the mass and the length and the mass of the beam, okay, so I didn't write down the beam mass. But now I get it. Beam mass is big M. Magnet mass, or whatever it is, in this case is little m, right? But there's your moment of inertia and the kinetic energy. One half I omega squared. So you can easily, from the quantities we have here, reason out the change in potential energy, which is pretty straightforward. Understand that the beam has a moment of inertia. It's given by a formula that you're going to learn to derive. Very simple, single integral. Okay. And the mr squared for this, because remember, moment of inertia is the sum of all the mr squares. Okay, we did that last time. I hope that's locked in because that's what it comes down to, and that's why you do the integrals you do. That's it. In this case, made it unconstrained, moved at this distance from the axis of rotation. It always has moment of inertia, ml squared over 4. So having worked this out, you just plug your mass, your two masses in the appropriate places, length in appropriate place, and you get a moment of inertia. Then you can calculate omega, because you got I, you know what your kinetic energy is. So that that omega F, so that the angular velocity here omega equals 0 in this position. Omega equals omega F in this position, okay? So you have 1/2 I omega F squared equals mgh. Now, I really didn't work out H though, did I? But we said it. I mean, one of you said it earlier, I think you said it. Okay. So there's your H. That's your situation. Put your numbers in, everything works out. Okay, show you one other quick instance of this sort of thing. Okay, one more thing we looked at is this contraption. Okay, it's pretty well balanced. If I spin it, it has a fairly constant angular acceleration. You see it's kind of speeding up, slowing down a little bit because things are off center just a bit. It wasn't possible, given the time and tools that I had, to position these exactly. I could get the machine shop probably to run me something like this with holes in it, but okay, it's just a piece of styrofoam. Got a bunch of bolts in it. There's the head of the bolts, bunch of carriage bolts, and there's the other side where the nuts are tightened down. And the bolts are as close as I could get it at 10 centimeters from the axis of rotation, and 7 centimeters and 5 centimeters, I think. Styrofoam has a known thickness and it's uniform and a known diameter. The bolts can be unscrewed and weighed. I forget what they weighed, 12, 14 grams, I think, for the nut, each nut and bolt. So we could easily calculate the moment of inertia, assuming that each bolt is a point mass, which is not a bad approximation in this case. We just do the MR squared for each of the bolts here, and then multiply by 4. And we get the moment of inertia due to the bolts. And then we can take the mass of the styrofoam, either by figuring out what the density of the styrofoam is, pretty thick, pretty solid styrofoam. Or we take the bolts out and weigh it, or take one bolt out and estimate the mass of the axis and so forth. So we get a pretty good idea what the moment of inertia of the styrofoam disc is. And it'll be 1/2 mr squared, for m is the mass of the styrofoam, r is the radius. That's the expression for the moment of inertia of a uniform disc. And we'll probably set up the integral and derive that one because it's pretty easy. Okay. And now we can do the same thing with this that we did with that beam. We just slap that magnet on there. Okay, and it let me release it. It released itself. Let's try again. Okay, so get the magnet up there, release it. And the thing again undergoes some very close to simple harmonic motion. There's some friction between my fingers and the axis, so this thing doesn't go as long as the beam with the good bearings does, but it goes a while. We could actually measure the period of the motion and do all kinds of things that we're going to do later. We'll be looking at this in lab, but it's a situation that's totally analogous to this. We have a change in potential energy simply due to the change in potential energy of the magnet, which is trying to come loose. Okay, it drops a certain distance. And most of the potential energy loss gets converted to kinetic energy. Some is used to overcome the friction. We can actually spin this thing. Now there's some thread on it, so it's not going to, but we can see how long it takes to come to rest from given angular velocity and figure out the acceleration and figure things out about the torque and all that stuff. That'll be coming up in homework this weekend. So when we study this in lab and similar situations, beams and so forth, we'll be able to corroborate some of the analysis we've already done. And then we'll be able to do maybe some more creative things.